I want to talk about the proof of this theorem, and it has two directions. It's if and only if. So I want to have to show that if f has an inverse, then it's one-to-one and onto. And then conversely, I also have to show that if f is one-to-one and onto, it has an inverse. Okay, so let me just show one of the directions first. Let's suppose that f has an inverse. Okay. So suppose f has an inverse, and we call that inverse g, and the inverse has to always go from the codomain to the domain. Okay, and then by definition of the inverse, we know that f undoes g and g undoes f. Okay, another way of saying that is g composed with f equals the identity, and f composed with g is equal to the identity, but they're identities on different sets. Okay, so this one's on y and this one's on x. X and y. Okay, so now we want to prove that f is one-to-one and onto. Okay, so let's do one-to-one first. What does it mean to be one-to-one? Well, anytime it has the same output, the inputs must have been the same as well. So let x1 and x2 be in the domain of f, and assume they give you the same output. So what we want to conclude is that they actually were originally the same input. And that's what it means to be one-to-one. Okay, so how do we do that? Well, we can just take g of both sides. Okay, g is our inverse function. So we make use of the assumption. So take g of both sides. You get g of f of x1 equals g of f of x2. Okay, and because g undoes f, this here is exactly x1, and that there is exactly x2. Okay, and then we've shown that f is one-to-one.